Now this item here is a capacitor, and capacitors come in all shapes and sizes, so go from a fairly large one to a really large one. But what I'd like to do now is actually sort of have a look at what's inside one of these components. So now what I can do is take out the inside, and this is the inner part of a capacitor, and what I can actually do is I can start to unwind it. Now there's this, I wouldn't necessarily advise you doing this, but what I'm going to do is just start unravelling what's inside. So as I unwind this, what we can find are there are these two sheets of metal. For some reason, the insulator here absolutely stinks. It's kind of dielectric. Okay, but basically, this is a construction of a capacitor. What we have are two plates, which are separated by an insulator. How does that work? How does it store charge? What's it actually used for? Well, that's what this video is all about. Now, I'm not sure exactly what the chemical was between those plates, but it stained my fingers yellow and it absolutely stinks. But effectively, with a capacitor, what we have are two plates which are separated by an air gap or perhaps by an insulator. And the circuit symbol for a capacitor represents it. So here we have those two metal plates, like I unravelled before. And this is kind of part of a whole circuit. And the reason that, in order to kind of get more capacitance, we need a bigger surface area. So what we do is we actually wind up these two parallel plates, actually when we put them inside one of our capacitors. And I'd like to spend this video looking in a bit more detail at what capacitance really is. Now this is my circuit symbol for a cell. And on the cell we have the positive and the negative end. And what I'd like to think about is if we have this cell, I'm not going to think about the conventional current which flows from positive around to negative, but I'm going to consider the flow of electrons from the negative end round to the positive end. Now, if I attach a wire to the end of each side of this cell, like this, what's going to happen is that all the electrons which are at this end, they want to repel from all the other electrons. And these electrons are going to spread out along that side. And then the electrons in this bit of the wire are going to be attracted towards the positive end, leaving this area to be a region of positive charge. Now if I take this wire and I make it longer and I kind of loop it round a bit like this, that just gives more space for these electrons to spread out. And again, they're going to repel as much as they can. And again, all the electrons in this part of the wire are going to move around to the positive end. So effectively what we have is this distribution of charges a bit like this. Well, I can keep that effect going by rather than just having two ends of wire which are kind of pointing towards one another. What I can do is I can make that wire bigger and flatter. And what happens now is that, again, all these negative charges spread out as much as possible, but when the charges are here, the negative charges are going to be attracted towards the positive end over here. And what we get then is effectively a region where we have lots of negative charges all on this plate here, and here this is where these negative charges repel other negative charges, and there we have a region which is positive over here. And effectively what we have here is our capacitor. Now our capacitor is two plates which are separated by an air gap, and that means, I guess, truly there's not really a complete circuit, but what we can still have is the flow of current. When we first set something like this up, we close the switch, then we have a small time when current is actually flowing around that circuit even though it's not complete. The other thing we can look at is maybe the total charge on this thing here. Now remember, charge has the symbol Q. Well, the total charge that we have on these two plates, and also perhaps maybe the potential difference that we have across them, so perhaps we had a voltmeter set up across that. These two factors tell us about what we call the capacitance of this plate. Now capacitance has the symbol C, and there's a reason why we often get confused with this. The reason being that charge has the unit of coulombs, which is C, but C is also the symbol for capacitance. But capacitance has another unit, which is the farad. Okay, whereas potential difference not only has a symbol V, but it also has the units of V as well. Now these capacitors I showed at the start of the video, what they all have is a different capacitance, which is, that means they can store a different amount of charge. And effectively capacitance, which has the symbol C, this is defined as the capacitance is the charge stored per unit PD across it. Not per unit volt, which is a unit, but the unit PD across it. And therefore C is the Q over V. And effectively what that means is something which has a higher capacitance can store more charge for a certain potential difference which is actually across that component. Now, I mentioned here that capacitance has a unit of farads. Okay, and a farad is actually quite a large unit. And when it comes to looking at these real-life capacitors, if I just look on the side, this one here, I don't know if you can just see it, it's got a value of 100 microfarads. So this thing here, even though it's rated up to maybe sort of 63 volts, so quite high voltage, you can apply across it. The actual capacitance is a microfarad, so not much at all. So what else do we know about this? Well, we also know then that 1 farad is the same as 1 coulomb per volt. And then that gives us our definition of what the unit of capacitance truly is. So in my next video, I look at how capacitors behave perhaps when they're connected in series or in parallel, and also what they're actually used for. What's the point in you learning about them at this stage?